the entirety of the list without finding our search term, the algorithm will simply return a null value to let you know that the item you're searching for cannot be found in the list. The binary search is way faster and more efficient than the linear search, since we are drastically cutting down the amount of elements we have to look at, making the program run faster. In almost 99.9% of cases in which your list is sorted, the binary search is going to return a result faster than the linear search. So, if you have a sorted list, your best option is to go for binary. As for efficiency, the binary search is O log n for the worst case scenario, which could be confusing if you don't fully understand logarithms, but all you need to know is that it is way more efficient than the linear search. Its average scenario is actually also O log n as well, which again is infinitely times more efficient than the linear cases. Now, while there are other types of searching algorithms you can use, these two are the most common for both unsorted and sorted lists, so we will stop there for now. Up next, we're going to be covering one of the most confusing and important topics in computer science: recursion.
Let's start with the most important question. What exactly does recursion mean? In programming, recursion refers to functions that repeatedly call themselves, meaning that in the instructions that occur within a function, one of the instructions will be a call to that same function you're already in. In the extremely primitive example on your screen now, you can see we have some function which, in the confines of itself, calls itself. A recursive function will usually take into account some integer as an argument, and will use this to carry out some instructions, modifying the integer that was entered, before calling itself again with that new integer as its argument. To better understand these functions, let's discuss the basics of how we go about programming one of them. A really good and easy example of a recursive function is one which sums up all numbers from 1 to n. So let's make a recursive function that does just that. The first thing we need is the actual function, and we're going to make it an integer function, which takes an integer n as its argument. The reason we do this will be explained later, but for now let's move on to the base case. A base case is simply a definite value which all recursive statements, the ones that are being repeatedly called as we go through the function, try to get towards. At the beginning of the function, we test a value that was passed in by the argument against the base case to see if it is satisfied. Usually, these base cases are some requirements, like if n, as I described before, reaches a certain value or is equal to a certain value. It is extremely important that the base case is set to some requirement that n will eventually meet, for the same reason that it is important to avoid an infinite loop. We do not want a Stack Overflow error to occur. For example, if our base case was to stop calling the recursive function when n was greater than 100, and if it is not, we will call the same function again but with n minus 1, and we started with n as, say, 99, we would never reach the base case, and the recursive function will repeatedly call itself over and over again, subtracting 1 from n, and hoping that somehow it will eventually be greater than 100 until your computer crashes. Not fun. So anyways, back to our recursive sum example. Let's make our base case when n is less than or equal to 1. This way, we can start at some positive integer n, and subtract from it until it is less than or equal to 1, in which case we can exit the recursive statement. Cool. Now, if n is not less than or equal to 1, what we want to do is return the sum of both n and then the returning value of our recursive sum method minus 1. Why do we add n and the function call? Well, let's actually go through the function as if we were the computer and see why. We start with a call of recursive sum with n equals 3. We know that 3 is not less than or equal to 1, so now we try to return a recursive sum of n, which is 3, and the returning value of recursive sum with an n of 2. We don't know what the returning value of recursive sum with an n of 2 is, so we have to go through the function again, only this time n is 2. Again, n is not less than or equal to 1, and so this function will go through the else statement and return 2 plus another recursive statement, in this case the returning value of recursive sum with an n of 1. So once again, we have to go through the recursive sum function to get that value that will be added to 2, and then returned and added to 3, and then returned. Hang in there, we're close. Now in this function, n is less than or equal to 1, and so we return n, which is 1. Now we take that n, which again is 1, and that is what gets added to 2 in the previous function call and then returned. So this would return 3. Now this 3 is what gets added to the first function call, which is 3, and so it becomes 3 plus 3, which is 6. And finally, after all that time, we get 6 returned from the function, which, if you've been following along at home, 3 plus 2 plus 1 is, indeed, 6. Now this may seem like a waste of time since 3 plus 2 plus 1 is not a hard operation, but to those of you saying that, I ask you to please give me the sum of all the numbers from 1 to 3,567. Godspeed. Now recursion is a very difficult concept to wrap your head around, so if you're not 100% comfortable with it at the moment, feel free to rewatch this section of the video in order to better familiarize yourself with it. Alright, cool. Now that we have a little background on recursion, let's talk about why it works so well. Now to understand why and how recursion works, we must first understand what a stack is. A stack is a data structure that contains all of the tasks you instruct your program to complete. Based on a certain method, your program will then carry out the tasks you give it. It's called a stack because if we start another process before the previous one completes, the process is stacked on top of the other one, such as the animation on your screen is showing now. Programs we write will follow the LIFO structure. For those unfamiliar with accounting, LIFO means last in, first out, or the last item put on the stack will be the first one removed from it. Essentially, every time you ask your computer to complete a task, that task is added to the stack, and will be the first one to be resolved. Think of it like a stack of stones. You can keep adding stones on top of your pile, but in order to get to the one at the bottom, you must first remove all the rocks on top of it. Now when your function continually calls itself without end, without a base case, like in our infinite loop example, then the stack will never be resolved, as items will be continually added to the stack without any of them ever being completed. In this case, the memory allocated to the stack exceeds the maximum allowed, and a stack overflow error occurs, resulting in your program crashing. Think of this as if you're doing chores, and before you complete one chore, you get called to do another chore, and then before you can complete that one, you get called to do another one. Since you keep stacking tasks, or chores, on top of one another, the stack of tasks will never be completed, and you will probably die before ever finishing all of your chores. This is the same logic that makes infinite loops crash your program. Recursion works on these same principles. The initial call makes a second call, which is added to the stack, and now that one must be taken care of first. But in that one, another function is called, which gets added to the stack, and so on, until you reach the base case in which you slowly start going back down the stack. In conclusion, recursion in general is extremely useful because by calling the same functions repeatedly, it breaks down the problem into smaller sections and results in the program being more efficient. Small parts of problems are easier to solve and less taxing to compute than the entire problem at once, and the computer can combine these small solutions into the whole solution at the end.
Now, as we wind down our Introduction to Programming series, we want to take some time and go over some of the soft skills needed to be a successful computer scientist, since it's not all about writing code. In fact, many professional computer scientists will tell you that the majority of their job is spent thinking about code, rather than actually writing it. This is because much of programming boils down to problem solving. How do we optimize this system? How can we make this feature for our app? What type of movement do we want for our game, and how can we program it? The harsh truth is that no good program has ever been written simply from the programmer getting the prompt or idea, sitting down, hopping on an IDE, and starting to write code. There are many tasks we should go through beforehand in order to plan out our code, so we ensure that when the time comes to program, it's a clean and easy process and not riddled with mistakes and bugs. This is where pseudocode comes into play. Think of pseudocode like this. If you wanted to take a family trip to the Grand Canyon, would you simply hop in your car and drive off and figure out things later? No, because that would be ridiculous. Instead, you would spend some time planning out the trip. What sites or places do you want to visit? What hotel reservations are you going to have to make? What kinds of things are you going to do when you get there? What routes or highways are you going to take and why? All of these things must be determined before you can even think about hopping in your Ford Explorer. So how does this translate to pseudocode? Well, think of our family trip to the Grand Canyon as a program. Programmers use pseudocode, pseudo meaning not real, and code meaning code, as a means to plan out their programs before they write them, just like how we planned out our trip before going. They throw away syntax and naming conventions for variables and just focus on what they want the program to accomplish and how they plan on doing that. Pseudocode is very similar to constructing an outline for a paper that you're writing. You write down the main topics of the essay and plan out your major talking points, but you don't worry about the nitty-gritty details of it all, such as word choice, grammar conventions, and proper formatting. By doing this, we allow ourselves to think freely and not worry about stressing the small stuff, at least not yet. Alright, now that we know what pseudocode is, let's talk about how we write pseudocode. You see, the best part about pseudocode is that it can take the form of many different things for many different people. Each computer scientist has their own methodology for planning out their code, and there are probably hundreds of different methods of writing pseudocode that are out there today. Today, however, I'd like to focus on 3 popular ones that I think you might find to be extremely useful. The first of these is known as flowcharts, and mainly they can be used to think through the process of a particular function. A flowchart is fundamentally a graphical representation of a function and how it might flow. Many programmers do this and lay out the conditional statements and loops that they want as different blocks in the flowchart, connected by arrows and charting out every path of their function. From there, it's extremely easy to create test cases and follow them through the flow of the function through the different blocks and arrows. For example, we could have a flowchart that goes something like this. A user enters in a number, and if the number is 8, I want the program to return true. However, if the number is not 8, then I want it to return false. It's a great way to visualize what the function's overall purpose is, and also look for any errors that you may have missed when thinking about the function, such as a missing path. It also abstracts the programming statements up to simple blocks, making it easier to modify or change completely. The best part is that when you have finished testing cases, you can simply convert the blocks into programming statements and you have a well-written function without any debugging. Another popular pseudocode technique that is often used is to simply write out what you want your code to do chronologically. Don't necessarily think about what programming statements and functions you want to use, just jot down, from start to finish, what it is the program you're writing is going to do step by step. For example, let's say you're making an app that takes in 2 numbers and divides them. The pseudocode for that would look a little something like this. First, I want to prompt the user to enter a number, and then I want to wait for the user to enter in that first number. After I get the first number, I want to again prompt the user to input a second number. Once they do, I complete the operation by dividing the 2 numbers entered and returning the result back to the user. This all seems like it would be common sense, but remember that oftentimes we're not going to be working with simple multiplication or division functions. We may be working with full-scale games, algorithms, or user interfaces with many different options. This method allows you, the programmer, to not get bogged down with the syntax and conventions that you have to follow. You're simply making a note of what the program's ultimate goal should be, as if you were explaining it to a friend of yours. This method really lets you plan out everything that needs to happen in your program in order for it to run smoothly. It also ensures you don't forget about a piece of an algorithm or a certain function that you need to write in afterwards. And the final pseudocode strategy that I'd like to talk about to you today is writing out the main features you want the user to have when using your program, and what functions or smaller programs you're going to need to complete these features. Let's do another example. Say you're making a banking interface, and on startup, you want the user to initially have 2 options. They can set up a new account or log into an existing account. From there, if they log into their account, then you want them to have the functionality to withdraw money, deposit money, take out a loan, or pay back a loan. If they decide to set up a new account, you want them to be able to create an account, store their information in a database, and then access all of the features that a returning member would have. This may look very similar to the flowchart method, the only difference being that this is abstracted one level higher over an entire program rather than just a single function. If you really wanted to, you could also create a flowchart that would go through the functionality of all the 4 methods described above. Setting up a hierarchy, like seen on your screen now, makes it easy and clear to see every function and interface you're going to have to make. This prevents you from having to try to shoehorn a function or feature into an already finished program at the last second, which is not a very fun experience in the slightest. So there you have it, 3 pseudocode strategies you can use to plan out your code before you even start writing any. The flowchart method, which is good for thinking through the flow of a certain function. the write-up method, which is good for getting the general idea down for a program, or the functionality planning method, good for listing out the functions of a certain program. You can use all of them, none of them, a mixture of them, or even disregard these and find and create your own pseudocode methods. The main goal here is to drastically minimize the amount of errors that occur during your program and relieve a lot of stress on your head. The importance of pseudocode cannot be stressed enough, and if you don't believe me, I urge you to try to complete a large project without it.
Okay, so if you've watched the series up until this point, you've gotten a pretty good understanding of many aspects of programming and also how to plan out your programs. Now it's time to go out into the real world and write some actual code. But what kind of program? I can hear you asking me. And the answer is truly whatever you want, really. As I'm sure you know by now, you can program just about anything you have on your mind. Anything from simple games to complex software. This video has equipped you with the basics that are going to need to be used in pretty much any program you decide to write. But that doesn't mean that every programming language is perfect for every application. Each language has its own strengths and weaknesses, and choosing the right one is very important for making it easier, and sometimes just even possible, for you to program what you want. So that's what we are going to be talking about now, choosing the best language for what you want to accomplish. Now, we talked earlier about low-level versus high-level programming languages. In case you forgot, let's do a quick refresher. Higher-level programming languages have a higher level of abstraction from machine language, that series of zeros and ones from way back when, while lower-level programming languages have a low level of abstraction from machine language. For example, block programming, where you can drag and drop programming statements together like 2D Legos, would be a high-level language, as it does not take a high level of understanding of the inner workings of a computer to program it. The theoretical highest level of a programming language would be if I could just write down what I wanted the computer to do in simple English, and it would just work. But, sadly, that doesn't exist yet. On the other side of the spectrum, the lowest level programming language would be just feeding zeros and ones into the computer at supersonic speed, which would be almost impossible and extremely absurd. So, how do you choose what type of language is best for your needs? Well, it depends on what you are trying to do, as sometimes you need very specialized languages to get done what you want. The world of computer science is vast and contains many fields, so trying to cover everything in one language would be impossible. This has led to the creation of hundreds of different programming languages, each designed for a specific task. Right now, though, we'll cover some of the most popular languages and their uses. Now, if you are trying to design a website, using HTML and CSS is probably your best bet. HTML is a markup language that is designed for writing the content of a website, while CSS is great for designing the style of the website. You interact with HTML every day, and you can even see it right now if you right-click and hit Inspect Element. This will truly show you how complex HTML and CSS can be. Maybe it would be best for you to use a scripting language. A scripting language is a language that has many commands for you to use, and that can also be run without needing to be compiled. Scripts can be faster to write than most programs, and tend to be easier to port between operating systems, allowing for cross-platform support. Scripts can also be used with websites, oftentimes adding to the overall user experience of the site. If you want to go into web design, this might also be a path for you to go down. Examples of scripting languages are Perl, PHP, Ajax, and JavaScript. For most programs, you could probably use a general-purpose language. General-purpose languages, as they sound, have a wide range of applications. Usually, these should be your go-to languages. Examples of general-purpose languages are Java, C++, and Python. They each have their own different benefits over one another. Java is very useful for developing games and interactive web pages. Python can act as a scripting language for web programming as well as writing applications and data analysis. And C++ tends to be used for writing applications and system programs. They all have a variety of packages that you can import and use to achieve the functionality you need from them. While selecting the right general-purpose language for your big projects is very important, for most of your programs, any one of them will work. It really comes down to preference. Get to know each language and decide which one's syntax rules you like best and find most comfortable. If you get to know one general-purpose language really well and enjoy programming with it, you can apply it to just about any of the programs you plan on writing. Personally, I tend to use Python for most of my projects. This is mostly not due to any functional difference between Python and any other general-purpose language, though there are a few, but it is mainly because I find its syntax rules most convenient and easiest to write programs with. Overall, either you can consider the project you plan on doing and research and see which language boasts the most advantages for your purposes, or you can simply become comfortable with a language and use it for most of the programs you decide to write.
We'll now be looking at our final topic of this Introduction to Programming mini-series. You now have the basic knowledge of programming, which will take you far in any language that you decide to learn. You know some good pre-programming pseudocode strategies to help you design your code from the ground up, and you might already have a good idea as to the type of programming language you might want to start with. So what's the next step? How can I learn that language, and what applications can it be used for? Well, that's what we're going to be covering now, so let's just jump right into it. Starting with the biggest question, which is what is the next step? Well, now that you might know which type of language you might be interested in, research that language and find out whether or not you truly want to pursue that programming language. Most languages, like Python or C++, will have either an official website where you can read up on the language, or a Wikipedia page which will provide you with useful information in deciding whether or not you want to pursue that path. From there, the next step is to actually learn the language, which can be done right here on YouTube. While we have taught you the basics of any programming language, each specific language is going to expand upon these concepts, and so watching tutorial videos on a certain language is going to be very beneficial. I would start with an introduction series, like the one you're currently watching, but for the language you have chosen, and work your way through that series, picking up on the syntax and rules of that language until you become comfortable with it. Once you do that, you come to a crossroads. You know how to program in a certain language, but you may be completely clueless as to what to make in that language. Programmer's block can leave you uninspired and not want to continue programming, so I'd like to give you a few websites to help out. First is CodingBat, a completely free website which has hundreds of coding challenges in both Java and Python to help you refine your programming skills and even learn some new programming shortcuts and tips. This is great if you want to get better at improving your efficiency and need something to hone your skills as a developer. The next is CoderByte, which offers over 200 plus challenges that you can complete in over 10 different languages, something that is sure to help you improve. The final website I'd like to talk about is HackerRank, which not only provides programming challenges to keep you on your toes, but also provides support for you using your programming skills to find jobs or internships. These and many more websites exist solely to keep you interested in code and work on refining your skills to become better. Now, if you're a teenager watching this series in high school, I also encourage you to take programming classes in your high school. AP Computer Science Principles and AP Computer Science A are both amazing courses which can help you greatly in the future, and are also incredibly informative and important to colleges. Your school might also offer other classes in the field of computer science, including ones on data structures, game design, and data science. Any and all classes you can take to help expand your knowledge of programming and help you find your niche is going to be extremely helpful. As you can see, the world of code has now been opened up to you. These are just a few examples of where you can go from here, but there are many more we didn't talk about. You could get into GitHub and start contributing to projects. You could work on your own projects and collaborate with others. The possibilities are endless. The next step is up to you. This concludes our Introduction to Programming mini-series. We hope you enjoyed watching it as much as we enjoyed making it. If you enjoyed the series as a whole, consider subscribing to our channel, Null Pointer Exception, which will be linked in the description, for more content like this coming soon. Thank you so much for watching.